Okay, so I'd like to start off with a sort of a warm-up. So I'd like you to graph the function that's the square root of negative x plus 2. So using the translations and reflections that we introduced last time. So the function the square root of x looks like this. Okay, and so I want you to use that and then try to get the graph of this function. Let's call this function h. Okay, talk to somebody nearby on what you're thinking. Okay, anybody want to tell me what I should draw here? Or do you want to talk a bit longer? I feel like people are still talking. Talk for just like a bit longer. Okay, anybody want to say what they're thinking? I forgot my 20-sided die. Yes, Stella.
We're thinking that it would be reflected across the y-axis.
Be what?
Reflected across the y-axis.
Reflected across the y-axis.
And then also, I think move to the left by 2.
Move to the left by 2. So square root. This is probably 1. So move to the left by 2. Okay. Anybody else? Yes.
Wouldn't it be moved to the right by 2?
Would it be moved to the right by 2? Let's see. So flip here and move to the right by 2. So that's another possibility. Let's call this one 1 and this one 2. Okay. Why do you think it's moved to the right by 2?
Just because if you plug in 2 for x, you get an output of 0. And so that would make sense.
Okay, yeah. So sort of like empirically, you can see that this function actually works for the number 2, right? So yeah, this one is kind of a tricky one. Yeah, and in fact, this is this one on the right. The number 2 is the right answer, and I think there's probably the way to think about it is like this. So one way, basically, it's not just one move, not just one translation or reflection involved, right? Not just one operation involved. There are 2 operations, right? So I think maybe the way to think about it is like this. So, right, we've got this function f of x equals square root of x, and we want to get this function negative x plus 2. Okay, so maybe the way to think about it is to introduce an intermediate function. So g of x being, say, square root of x plus 2. Okay. So why do we introduce that guy? Well, because that's just one translation of the previous guy, and we can get from this one to the next one via reflection, right? So this is like halfway between, right? You can, if we take h of x can be expressed in terms of g of x, right? It's g of negative x, right? Everybody see that? Okay. So you can say, okay, now then I can think of this. What are the graphs going to look like? Well, I have this is my graph of f, and then I'm going to shift 2 to the left, right? Because time is step forward 2 units, right? So you move it over to the left, right? Right. So that's the graph of g, and then the graph of h is going to be the reflection of that. Right? And so you get that. That's the graph. Okay. So that's one reasonable way to think about it. The thing that's a little bit tricky here is that you can actually do this in a couple ways. You could also say it like this. You could do it like this. You could say, let me let g of x be negative x. Okay. And then h of x, I'm sorry, let me let g of x be f of negative x. Right? And then my h of x is going to be g of what? I want to get, right, this is going to be the square root of negative x plus 2, right? So I want to get g of, this is going to be g of x minus 2, right? X minus 2, because g of x minus 2 is f of negative x minus 2, which is f of negative x plus 2, right? f of negative x plus 2. So that's right. Okay. So in that case, maybe you want this. Maybe you think, okay, I'm actually going to realize this as a reflection followed by a translation rather than a translation followed by a reflection. Okay. You see that you get, this is your f, right? And then your g would be just a plain old reflection, right? And then your h would be moved to the right by 2, right? Because time has slowed down by 2 units, right? And you get this. Okay, and you see you get the same thing. Okay, so these are, it's just, we're just stacking these operations on top of each other. It's a little bit tricky, but it's, don't be intimidated. It's just 2 simple things stacked on top of each other. Okay. Any questions about that? Okay. This was the one where I said I didn't have a good way of explaining, so I think maybe this is clear. I hope. Okay. Okay. So there's one sort of digression in. So that was in section 3.4, and there was something I left out. I didn't get to in section 3.5, which, remember, we were doing composition. The main thing was composition of functions, right? We did like combining functions using arithmetic, which was kind of trivial, and then composition of functions, which is non-trivial. Okay. So so the thing that we didn't get to, and this is sort of a digression. This is not really that important for us. Although it has its place in mathematics. So it's basically this thing called iteration, where you take a function, and then you feed that function back into itself. Okay, so you take f of x, and then you take f of f of x, right? F of f of f of f of x, and you keep on going. Okay. So you create this sort of like infinite composition, f composed with f composed with f composed with f, right? You do that say n times, and then you let n tend towards infinity, okay, and see what happens, right? So this is you're iterating the function. Those of you who've heard the term fractals, fractals are I think often generated in this way. If you want to see cool things on the internet, look at, say, Mandelbrot set or the Julia set. These and those are actually generated via iteration. Unfortunately, I don't have time to show you a movie, but it's pretty cool to see. They are things with sort of infinite complexity. So like no matter how far you zoom in, it just stays equally complicated. Like most things, right? Like something like this, say, right? You're like, okay, it looks complicated from a distance, but when you zoom in on it, right, it doesn't look that complicated. It's like a line, right? It's very, right? Things, often things when you zoom in on them, they get less complicated. But these things have sort of infinite complexity. No matter how far you zoom in, they stay complicated. Okay. Anyway, yeah. So the digression is about iteration, and there's sort of a graphical, and we saw some of this earlier. Graphical representation of this. So for example, right, you can have a function like this. So here's your function, y equals f of x. And we saw this earlier, so maybe I don't even need to talk about this. But this is when we were doing those graphs at the beginning. So if I take a point, so this is the line y equals f of x, the graph of y equals x. Okay, so you have your function, and you have this line y equals x, and you take a point x naught on it. Okay, then this height is of course f of x naught, right? And then if we project sideways, go perpendicularly here, right? So this is perpendicular. We go perpendicularly to this line, then we get the point f of x naught, right? Because the y coordinate is f of x naught, and the x coordinate is equal to, right? And then you remember what we did last time. We're going to go from there. Now we project vertically to the function, and the x coordinate stays the same, but the y coordinate has to be f of the x coordinate. So we get this is f of x naught, f of x naught, right? And we keep on going, right? So we go to the line, we go to the y coordinate, we go to the function, we go to the line, we go to the function, we go to the line, we go to the function, we go to the line, we go to the function, we go to the line, we go to the function, we go to the line, we go to the function, so on and so forth. And in this case, it actually converges. That actually converges to as you head off towards infinity, it's going to get closer and closer and closer to some point. Okay, we call that convergence. Or say that it could this thing converges to some value. Okay, that might not happen. It could be that your function is such that that when you iterate it, it just keeps on going off towards infinity, right? You could have something like this, right? And this is sort of dumb, but you could have something like this where you start off with your function, you go to the line, you go to the function, go to the line, go to the function, go to the line, and you head off towards infinity, right? It doesn't have to be so nice and always end at a finite point. But anyway, so that's all we wanted to show you here. That there's a way of graphically interpreting this iterative process. Okay. And you're not going to learn it now, but there's something called Newton's method, which is a way of using iteration to solve problems. Like you can calculate square roots using an iterative process. So like, oh yeah, here's an example. And you don't have to know this, but it's just for entertainment. If you have this function, 1/2 quantity x plus 3x 3 over x n quantity, then oddly, if you start off with any point and you iterate this function over and over, it's going to end up at the square root of 3. Okay. So yeah, so this iterative process can be used to solve problems, in fact. And Newton was the one who, well, maybe, yeah, at least his name is on the method that uses this process. Okay. Anyway, this is, in the grand scheme of pre-calculus, this is just a minor amusement, I'd say. Unless you want to go into applied mathematics, in which case this is a really important method that leads to all sorts of other methods. Not that I know anything about applied mathematics. Okay, how is everybody? You guys okay? Okay, good. Okay, so did I tell you my daughter's reaction to my? Did I tell you the story about, like, I explained all this stuff to my daughter and she said I understood this perfectly? No? Okay, so the other day, over the summer, my daughter was, for some reason, decided that she wanted to study calculus. Okay, and then so she was studying calculus over the summer, and no, that's not right. Completely wrong story. No, this was during last year, during the school year, that's right. And she had come home and was talking about the dot product. And I was like, oh, the dot product. You know, this actually, she's like, what is this dot product? And I, of course, lit up and I was like, oh, you want to know? Here's what the dot product really is. And I talked to her for like 10 minutes, explain, how the dot product works and its, geometrical, interpretation. You go all the way down to the law of cosines and you come out of the end of this tunnel and then everything works out perfectly, right? And then I said, was that okay? And she said, I understood that perfectly. I was like, all right. And then she said, sarcasm. So that's kind of my experience as a teacher. Okay, I'm not hoping you guys are getting it, but who knows? Maybe you guys just say sarcasm. I can't. Okay. Yeah, and then over the summer she did study calculus, which was kind of kooky. Yeah. Okay. 3.6. Inverse functions. Yeah, my daughter's a workaholic. Much more than, much harder working than I am. By far. Okay. Okay. So let me start off with a question. Okay. So first off, is this the graph of a function? No, we said this before, right? This is not the graph of a function. Right? Why not? Because there are so many points, because you can find some bad point that gets mapped to multiple values, right? In fact, it has lots of bad points that get mapped to multiple values. Okay, right? So you would say it fails the vertical line test. Right? The vertical line test says that when you draw a vertical line, at most you can hit 1 point. Right? Okay. Second question. Suppose I have the graph of a function. Is the reflection of the graph of a function the graph of a function? And the reflection across the line y equals x. Okay. So you have the graph of a function, and then you reflect it across this line. Is is it still a graph of a function? Okay. You can draw some graphs and reflect them, right? So if I draw, maybe I draw this graph and I reflect it, and it still looks like the graph of a function, right? Draw some other things and see if you believe, see if you can come up, if you have an opinion one way or the other. Okay, talk to somebody. Okay, who says yes? Still the graph of a function. Close your eyes, close your eyes. Everybody close your eyes so you won't feel embarrassed. Raise your hand if you think yes. Raise your hand if you think no. Okay. The answer is no. Yeah. Okay. So the reason is you could have a function that goes something like this. For example, just the x squared function. Okay. So when you reflect it, oops, that picture. When you reflect it, you're going to get this, right? So this is a function, right? This is the graph of f of x equals x squared. But this is not a function, right? This is not a function because it fails the vertical line test. Okay. Good. One person who noticed that. Yeah, so basically you say if it passes, so if it fails the horizontal line test, then the reflection is not a function. Right? Because if it fails a horizontal line test, then its reflection is going to fail the vertical line test. Let me say that again. If the original function fails the horizontal line test, then the reflected function is going to fail the vertical line test and cannot be the graph of a function. Okay. But if it passes the horizontal line test, then it's okay. Then the reflection will be a function. Okay. Okay. So now suppose you have a function. Suppose you have a function that passes the horizontal line test. Okay, so here we're just going to stick with with my example, right, you got something like this, and then you reflect it, and you get something like this, I think. Okay. Observe. There's a relation between the coordinates of, let's call this function and reflection. Okay. There's a relation between the function and its reflection. I mean, I could call this one function and that guy reflection because they're reflections of each other. But anyway, there's a relation between the coordinates of the function and its reflection. Yeah, actually, let me call this like f twiddle. So with a tilde on top of it. I don't know why the word twiddle is funny, but we use it in mathematics. So f twiddle or f tilde. So I'm going to call f twiddle the reflection. I'm going to call the reflection f twiddle. Okay. So there's a relation between the coordinates. Does anybody notice it? Like, if I have a point here, and that point is a comma b, can you tell me something about the graph of the reflection? Anybody see it? Please. The x and y are going to switch, right? Right. So here, right, if I have a b here, then I'm going to have ba over here, right? I'm going to have this point b comma a over here, right? Because if I take this triangle and reflect it, right, I get this triangle here, right? So that the x coordinate turns into the y coordinate, the y coordinate turns into the x coordinate. Okay. And so what that tells you is that, okay, so here, this guy was on the graph of f. So the y coordinate is f of the x coordinate, right? So observe, b equals f of a, so observe b equals f of a, right? Now, what is this BA? The point BA is on this graph. So what does that tell you? That tells you that the y coordinate A must be f tilde of B. Okay, so if I'm thinking about this function f as something with inputs and outputs, and thinking of f tilde as something with inputs and outputs. Oops. Inputs and outputs. Well, whenever I have a point a comma b, right, whenever f takes a to b over here, f tilde is going to take b and turn it back into a. Right? Right? If this point was, 5 comma 2, this point was 2 comma 5. That means that f maps 2 to f maps 5 to 2, and f tilde maps 2 to 5, right? So it undoes whatever f does, right? So there's a relationship between these two functions, and that is that they reverse each other's behavior. Okay. So f and f tilde reverse, so undo each other's behavior, right? It's like you build something and then this other guy comes along and just returns everything to the state it was right before you did all that work. Okay, so it's like this, they're your enemy or something. Okay, so these guys are called inverse functions. Okay. So we call such functions inverses. Inverses of each other. Right, so f tilde is f's inverse and vice versa. Right, f is f tilde's inverse function. Okay, and the notation is we write this for, this denotes the inverse function. Okay, so we put this -1 up here. I know it's confusing. People always mistake this. People always confuse this with 1 over f, the reciprocal. Okay, so if you see something like this, so warning, this means the inverse of f. If you see something like this means the reciprocal. Right, it means 1 over f. Okay, so there's some confusion in notation here. Yeah, Vivi.
Just to be clear, so that f tilde is the same thing.
Yeah, so I was calling it f tilde over there. It's really called f inverse. Yeah. Yeah. So over here, yeah, probably I should have called it f inverse, but it would have been confusing. Yeah. And you notice that, you know, f is the inverse of f tilde, right? So f is actually the inverse of the inverse, right? It's right, the inverse of its own inverse. So remark that f inverse is just f. So I tried to, introduce this idea to you graphically. The definition of it is usually done in terms of composition. So here's the formal definition. F and G are called inverses of each other, provided that f of g of x equals x for all x in the domain of G, and g of f of x equals x for all x in the domain of f. Yeah.
I had a question
Yeah.
about the graph.
Sure, yeah.
So they only become inverses of themselves when it passes the horizontal line.
You can only be an inverse function. You can only have an inverse if you pass the horizontal line test. Yeah, right. Because if you fail the horizontal line test, then your reflected graph is going to fail the vertical line test. So there is no inverse function, right? So our example was this thing here, right? We had something like this, like y equals x squared, fails the horizontal line test, which means that its flip is going to fail the vertical line test. Okay, but you notice, just as a digression, if we restricted ourselves to the positive numbers, then it would pass the horizontal line test, right? And this thing would then pass the vertical line test. And that makes sense because this is x squared and this is the square root of x, right? So yeah, this does have an inverse, the square root function, as long as we're dealing only with positive numbers, right? So you can kind of, even if you fail the horizontal line test, well, it may be that some restriction of u still passes the horizontal line test. Okay, so it's just a side comment. Okay, so yeah, so that's one example of a function and its inverse, right? So like examples 1, f of x equals x squared on the non-negative numbers, right? Then f inverse actually exists, right? The square root of x cancel out the square, right? And if you compose them in either direction, you're going to get the function that does nothing, right? If I take f of f inverse of x, well, that's the square of the square root, which is just x, right? And if I compose them in the opposite direction, right, well, then I'm getting the square root of the square, which is just the original non-negative number, as long as we're dealing with non-negative numbers. A simpler example, maybe I should have started with that, is say like this: f of x equals 2x. Then what's f inverse going to be? What function would undo multiplication by 2? Divide by 2. Right? So divide by 2 would undo it. Right? Yeah. Yeah. Let me just make a sort of remark here that it might make more sense to write the inverse in terms of some other variable, right? Instead of saying, right, so you could have the function goes from x's to y's, and the inverse function goes from y's to x's, right? So as not to be confused, because, you know, like, if my function is from student to grade, right, then student is x is a student, right? F inverse would be going from grade back to student, right? X would then be a grade and in a different domain entirely. So properly speaking, you really want to use a different variable here. But often in pre-calculus books, they just call it all x because they don't want to confuse you with other variable names. But yeah, it would actually make more sense to say, like, to call this f of y, f inverse of y is the square root of y, etc. Anyway, okay. More complicated example: f of x equals 2x plus 3. What's the inverse function here? I'll let you figure it out. See if you can figure it out. What function will undo f? Okay, turn to a neighbor and say something. Okay, anybody want to say? Aaron.
Is it x minus 3 over 2?
X minus 3 quantity over 2. Yep, that'll do it, right? Because you see that if we put this thing into there, right? If we put this x minus 3 over 2 into here, well, it would get multiplied by 2, which would get rid of that, and we would be left with x minus 3, right? So f of x minus 3 over 2 is going to be 2x minus 3 over 2 plus 3. sorry, let me call this y. Sorry, I'll leave it as x. Sorry. Okay, right, and so you would get x minus 3 plus 3, which is just x. Right, and if you did it in the opposite order, right, if you did it in the opposite order, you get f inverse of f of x. Well, that would be the input minus 3 quantity over 2, which you see is going to be 2x over 2, which is x. Okay, so let me sort of make that into a procedure. Okay, so how does one determine the inverse function? How does one determine the inverse function? If you know, right, if you know f is invertible, right? That is, i.e. has an inverse. If you know it has an inverse, how do you determine that inverse? Okay. Right. Right. So the question is, if we have a function f of x, how do we figure out f inverse of y? Right, the inverse function. Okay. So think we want some sort of object. And I'm going to just make it this box. Okay. We want some sort of object, right? So the box is the thing we're looking for. Okay. We want some sort of object with the property that f of that object equals y. Right? That's our goal, right? We want to find f inverse of y. We want to find the thing that if we put it in here, we get y. Right? Okay. So how do you do that? Actually, we know how to do that. We just solve the equation. Okay. So just solve the equation f of blah equals y. Right? Solve for blah. Right? And actually, I probably didn't need to even use this box. I could just say solve the equation f of x equals y. Right? Solve for x. Right? Solve it for x. Solve it for x. That's your f inverse of y. Okay. So like in the example that we just did, f of x equals 2x plus 3. F of x equals 2x plus 3. So you say, okay, I've got this equation, f of x equals y. I solve for x, right? Solve for x. We've done this many times before in this class. Right? 2x equals y minus 3. X is equal to y minus 3 over 2. Right? And that's going to be my f inverse of y. Okay, and that's you see that's what we got over here, right? The thing that the inverse function was take the input minus 3 quantity over 2. Okay. Yeah. Okay. So, right, like again, if we were right, if f of x were the squaring function on the non-negative reals, then you would say, okay, x squared is equal to y, and then you would solve for x. X is the square root of y, right? And so that would be your inverse function. That would be your inverse function. And you don't like using y as your input, once you get to this point, you can just switch everything back to x's if you feel like it. But really, you should keep it as y. So, second example, first example. Another one along the same lines. Let's say f of x is 1/3 x plus 2. Okay. Take a minute and see if you can figure out the inverse function. Okay, turn to somebody nearby and talk. Okay, so what's the inverse function? F inverse of y is what? Anybody? 3 times what?
Quantity y minus 2.
3 times the quantity y minus 2, right? 3y minus 6, right? And the way you get it is you say, okay, I just need to solve this thing for x, right? Because I'm looking for the x that gives me a y, right? I'm looking for, right? I'm looking for the x. I want f inverse of y, right? I want the thing that if I put it in here, I get y, right? So let's just solve this thing for it, right? Let's solve this thing for it. You get like 1/3 x equals y minus 2. And so x is 3 quantity y minus 2, or 3y minus 6. Okay. Last one. F of x equals x minus 3 cubed minus 1. Okay, anybody want to say what they got? Yes, Zoe.
The cube root of y minus 1 plus 3.
The cube root of what?
Y minus 1.
Y minus 1 plus 3.
Or plus what?
Plus 1.
Oh wait, no. Plus 3.
What?
Plus 3.
Plus 3. Okay. Let me work it out. So let's see. So we're going to set this thing equal to y, right? And then solve for x. So we say x minus 3, and we get y plus 1, right? And then we take the cube root of that, we get x minus 3 equals the cube root of y plus 1, and then we add 3 to that. So we get the cube root of y plus 1 plus 3. Right? So that's going to be our inverse function. Yeah, Beauty.
So I just have a question about the one you did before.
Yeah.
Why don't you just sort of output from the answer?
You can.
Yeah.
Yeah, that's fine. It's the same thing, right? So you could, yeah. Yeah, it's sort of doesn't make any difference. Okay, any questions? Okay, that's it. That's it for today. Don't forget, so we're having an exam next Friday. There are 2 other possible dates, but there were, each date had some opposition to it. And since I had already announced that the exam was next Friday, let's just keep it there. Okay. So yeah, exam next Friday. It will cover up to today's material. Yes, please.
Well, it'll take an hour long, or will it take some?
Will it take an hour long? It should take 50 minutes, right? This is a 50-minute class. Yeah.
So it encompasses the things that we did like on the last exam, you're saying all of it? It's-
No, I mean, in some sense, you can't avoid that, but it's not gonna do that intentionally. So, like as a side effect, right? Incidentally, we may have to use some of that previous material, but this is really an exam on the next material.
You don't need a calculator, right?
No, you don't. Yeah. Yeah. The only thing, basically, it should be very, elementary. The only things you need to calculate are just very elementary arithmetic. So no.